The main battle tank. For over a century, it has been the undisputed king of the battlefield, an iron fist of land power, capable of breaking enemy lines and striking fear into the hearts of its adversaries. From the fields of World War II to the deserts of the Middle East, the tank has been a symbol of industrial might and military dominance. There was a time when this symbol was also one of resilience, a machine designed not just to fight, but to be fixed. With basic tools and mechanical know-how, soldiers could bring these steel beasts back from the brink, right on the front lines. But that time is gone. Today's main battle tank, like the American M1 Abrams, is a technological marvel. It's a 70-ton Predator, bristling with classified armor, guided by satellite, and powered by an engine born from a helicopter. It is, without a doubt, the most lethal ground weapon ever created. But it has a fatal flaw, one that isn't found in its armor or its gun, but in its very soul, its complexity. We've spent 50 years in a relentless pursuit of the perfect, invincible tank. But in doing so, have we created a weapon so advanced, so sophisticated that it's become a logistical nightmare? A weapon that's too complex to fight, and almost impossible to fix on the modern battlefield. Why modern tanks are too complex to repair? To understand how we got here, we have to go back to World War II. The two most iconic tanks of the war weren't the most powerful. They were the Soviet T-34 and the American M4 Sherman. Germany had the technologically superior Tiger and Panther tanks, but they were complex, over-engineered, and constantly breaking down. The Allies and the Soviets followed a different philosophy. Quantity has a quality all its own. The Sherman tank wasn't perfect. Its armor was thin, its gun was initially underpowered, but America built nearly 50,000 of them. Its genius was its simplicity. It used a radial aircraft engine, similar to those found in planes of the era, and its components were standardized. A trained crew could swap out a Sherman's engine in a matter of hours, using a basic crane. A broken track pin could be hammered out and replaced. Parts were interchangeable. This meant more tanks were available for combat, more of the time. This was the gospel of mechanical simplicity, and it won the war. The T-34 was even more extreme. It was crude, uncomfortable, and built with loose tolerances, but it was tough as nails and could be repaired with a hammer and a prayer. Soviet doctrine accepted that they would lose tanks, but they could produce them and repair them faster than the Germans could destroy them. This philosophy, that reliability and ease of maintenance were just as important as firepower and armor, would define tank design for a generation. Even in the early days of the Cold War, this idea held on. Tanks got bigger guns and thicker steel armor, but at their core, they were still fundamentally analog. Mechanical machines, but a technological storm was brewing. One that would change everything. The Cold War, arms race, and the birth of complexity. The Cold War was a battle of ideologies, but it was fought in the design, bureaus and laboratories of the East and West. The fear was a massive Soviet tank invasion pouring through the Fulda Gap in Germany. NATO was outnumbered. They couldn't win a war of numbers like in World War II. The solution? Technology. They had to build a tank that could kill multiple Soviet tanks before being killed itself. This led to 3 revolutionary changes that planted the seeds of our modern complexity problem. First, the armor. Steel was no longer enough. The British invented Chobham armor, a top-secret composite material. It was a sandwich of ceramics, metals, and polymers. It was incredibly effective, but it was also a black box. You couldn't just weld a patch onto it. If a Chobham array was compromised, the entire massive block had to be replaced at a specialized depot. Field repair was out of the question. Second, the gun and its brain. To guarantee a first-shot kill, you needed more than just a good cannon. You needed a computer, laser rangefinders, crosswind sensors, thermal imagers for night fighting, and ballistic computers that could calculate a firing solution in a fraction of a second. This hunter-killer capability was revolutionary. A tank commander could identify a target, and the gunner could engage it, while the commander was already looking for the next one. But each one of these systems added a new layer of delicate electronics, wiring, and software, all things that hate vibrations, dust, and the brutal shock of firing a 120 mm cannon. This right here is the problem. In a Sherman tank, if your gun was misaligned, you'd use a wrench. In an M1 Abrams, if your thermal sight goes down, you're not fixing it with a wrench. You need a specialist with a laptop running diagnostic software. You've gone from a mechanic to an IT technician. And finally, the third and most controversial leap: the engine. When Chrysler designed the XM1 prototype, they made a radical choice. Instead of a conventional diesel engine, they chose the AGT 1500 gas turbine. A gas turbine like a jet engine offers incredible power for its size. It's quiet, giving the Abrams its nickname, Whispering Death, and it can run on almost any flammable liquid. But it comes with a crippling price. It's a logistical monster. It consumes fuel at an astronomical rate, especially at idle. We're talking gallons per mile, not miles per gallon. Its exhaust is so hot it can melt asphalt and is a giant shoot me, signed to heat-seeking weapons. And its maintenance is a nightmare. While you can, in theory, swap the entire power pack in about an hour, fixing the engine itself requires a near clean-room environment. It sucks in massive amounts of air, and any sand or dust acts like a sandblaster on its delicate turbine blades. The filters need constant attention. The dream of technological superiority had created a 70-ton beast with an insatiable appetite and a very sensitive stomach, the digital behemoth. Anatomy of a modern tank. So let's break down just how deep this rabbit hole of complexity goes. This isn't your grandfather's tank. This is a network on tracks. Inside an Abrams, there are dozens of line-replaceable units, or LRUs. These are sealed boxes of electronics. If one fails, the crew doesn't repair it. They run a diagnostic, identify the faulty box, and swap it out with a new one. The broken one gets sent back down a long supply chain to a depot, sometimes all the way back here in the States, to be repaired by the manufacturer. This sounds efficient, but it creates a massive dependency. The Army doesn't just need to ship 70-ton tanks to a war zone. It needs to ship a constant supply of these multi-thousand-dollar electronic boxes. And what happens when you run out of spares? Your multi-million-dollar tank is dead in the water because of a single failed circuit board. And then there's the software. Modern tanks are part of a network. The latest versions of the Abrams have the Blue Force Tracker, a system that shows the location of all friendly vehicles on a digital map. They can share targeting data and communicate in real time. This is called battle management. It's an incredible advantage, but it's another layer of complexity. It means software updates, cybersecurity vulnerabilities, and system integration problems. Sometimes a new piece of hardware won't talk to the old software. A glitch can cause the system to crash at the worst possible moment. We've seen this in other advanced weapons systems, like the F-35 fighter jet. The tank is now facing the same problems. So you have proprietary hardware, running proprietary software, protected by classified armor, all powered by a jet engine. The knowledge required to maintain this is immense. The days of a single, cross-trained mechanic are over. You now need an engine specialist, an electronics specialist, a communications expert, and a weapons systems technician. This isn't a crew. It's a Formula One pit team, and you can't deploy a pit team to a muddy trench on the front lines. Contrast this with modern Russian or Chinese designs. While they are also becoming more complex, many still cling to certain elements of the old philosophy. They use rugged, if less powerful, diesel engines. They often use autoloaders to reduce crew size, which adds mechanical complexity but removes the need for a human loader. Their systems are generally seen as less refined but tougher. It's a different trade-off, but one that acknowledges the harsh realities of war. The fundamental problem is this: we've optimized the tank for performance in a perfect scenario, at the expense of resilience in a chaotic one. We've engineered out the ability for the soldier to adapt and overcome with simple tools. We've replaced the wrench with a warranty call. The battlefield test. Reality bites. For decades, this debate about complexity was academic. The M1 Abrams dominated in the deserts of Iraq, where the US had total air superiority and a massive, uncontested logistics chain. But the war in Ukraine is the first time in decades we are seeing a large-scale, peer-to-peer conflict, and it has been a brutal reality check. We saw Russia's supposedly mighty tank armies falter, not just due to Ukrainian anti-tank missiles, but due to horrendous logistics and maintenance. Conscripts didn't have the training or the parts to keep their vehicles running. Tanks were simply abandoned on the side of the road when they broke down. This was a failure of the long tail of logistics. But this is not just a Russian problem. When the West began supplying Ukraine with advanced tanks like the German Leopard 2 and the American Abrams, the same issues appeared, but in a different form. These tanks require a completely different support infrastructure, different ammunition, different spare parts, and vastly different maintenance procedures. A Ukrainian mechanic who has spent his life working on Soviet-era T-72s can't just pick up a manual and start. Working on a Leopard's sophisticated electronics or an Abrams turbine engine, damaged tanks often have to be shipped hundreds of miles back out of the country to specialized facilities in Poland or Germany for major repairs. That's a tank taken out of the fight for weeks, if not months. The complexity designed to make them dominant in battle also makes them fragile in a sustained campaign. Think about it. The US military's model is based on expeditionary warfare. We bring our entire infrastructure with us. But in a defensive war like Ukraine's, where your industrial base is under constant attack, you don't have that luxury. You need systems that are resilient, that can be maintained with what you have on hand. The lesson here is stark. The best tank in the world is useless if it's waiting for a spare part that's stuck in a warehouse 1,000 miles away. The path forward, modularity, and mules. So is the main battle tank doomed? Not necessarily, but it has to evolve, or it will become a relic. Military designers around the world are realizing that the answer isn't just more armor, a bigger gun, or more complex electronics. The future might lie in a return to some older ideas, supercharged with new technology. One concept is modularity. Imagine a common chassis that can be configured for different missions. One day it's a main battle tank. The next, its turret is swapped for an anti-aircraft system or an engineering vehicle. This simplifies the supply chain. You're maintaining one type of engine, one type of suspension. If a component is damaged, you swap the whole module. It's the LRU concept, but for the entire vehicle. Another idea is to offload the complexity. Instead of packing every single sensor and system onto one 70-ton vehicle, you create a family of systems. The main tank becomes the killer, but it's supported by smaller, cheaper, and even disposable robotic mules. These robotic wingmen can scout ahead, draw enemy fire, or provide sensor data, allowing the main tank to be simpler, more robust, and more focused on its primary job. If a robotic scout is destroyed, it's a loss. But it's not a multi-million-dollar, irreplaceable loss like an Abrams. And finally, there's a renewed focus on diagnostics and artificial intelligence. Imagine a tank that can predict its own failures. A sensor on the transmission that says, I have 10 hours of operational life left before I fail. This allows for proactive, scheduled maintenance instead of reactive. Catastrophic repairs on the battlefield. It uses complexity to manage complexity. The evolution of the tank from a simple mechanical box to a digital behemoth is a story of ambition. The ambition to protect our soldiers, to dominate the battlefield, and to master the technologies of war. But this ambition has come at a cost measured in logistical chains, maintenance hours, and a dangerous reliance on a fragile industrial base. The Sherman tank was a reflection of the America that built it, a mass-production powerhouse that valued simplicity and reliability. The M1 Abrams is also a reflection of the America that built it, a technological superpower capable of creating systems of breathtaking complexity, but perhaps, just perhaps, forgetting the simple, brutal truth of war. The ultimate weapon is not the one with the most advanced features. It's the one that works when you need it most. The challenge for the next generation of military engineers is not to build a more complex tank, but a smarter one that rediscovers the forgotten wisdom of its ancestors. That on a chaotic battlefield, the ultimate sophistication is simplicity.